back. So in the last class, we discussed kinematic transformation. We saw what the degree of freedom is for a robot. And while discussing kinematic transformation, we came across homogeneous transformation matrix, for which we have already discussed what is translation matrix. So today we'll move ahead, we'll discuss rotation matrix, we'll discuss Euler angles, we'll discuss arbitrary axis rotation, and we'll continue further with rotation matrix. So let us move ahead. Let us just see what a pure rotation is. So if our object which is in space, which is in a global space of frame O, X, Y, Z, okay, so that is the frame, that is this one I am talking about. So if this object is in this space, if I rotate about x-axis by an angle theta to say, so let us see how to represent them, how to find out a transformation matrix which actually can achieve this. Okay, which actually can achieve this. So if NOA had the three unit vectors that was associated with a frame which was attached to that object, so N remains where it is, because that was aligned along with x-axis about which we were rotating, about which we are rotating by an angle theta. So what is going to change is O and A, that will be rotated by an angle theta. Okay, so that is what. So let us see. So what we intend to find out here is a rotation matrix 3 cross 3, that is the rotation transformation matrix, has capability to rotate the point PUVW, which is in object space, that is in object space. So if this is an object, with a position vector this from this corner, so this is UVW. So UVW is in this frame. So if this object rotates about one of the axes, so what will be the consequence of rotation on UVW when projected to, when seen from the global coordinate system, that is OXYZ. So OXYZ is the reference frame in open space about which rotations are happening, and OUVW is a frame which is attached to the object coordinate system. Okay, so that is there, and then I want to find out the new point location in the frame OXYZ after rotation which has happened to the object. Okay, so this is what is our intention. Let us see how this point initially was represented. Initially this point in the object space, initially the object axes were aligned with x, y and z axis of the OXYZ frame, UVW were aligned with this. So PU was equivalent to Px, that is the coordinate of, so Pu was equivalent to Px. Px is the projection of this point along x-axis. Similarly, Py was projection of P along y-axis, so this was equal to Pv. Okay, they are equivalent initially, and similarly Pw was equivalent to Pz initially without rotation. Okay, so let us come back to this. So yes, this was the point. Now I have to take projection of this point in order to find out. Let us say this has already rotated. Now I want to find out the projection of this vector along xyz axis. So that effectively will give me what I want. So by scalar product definition, we know if at all we have to project a vector along any of the axes, so I can directly take a unit vector along that axis and take the dot product with the given vector. So if I take dot product, that has a capacity to project that vector about which you are taking the dot product about its direction. Okay, so this is what, so Px, now I want to find out what is Px. What is that? This is projection of P along x-axis. So what was that? Projection of P along x-axis. I simply took a dot product and this is what is. Okay, So this is nothing but a dot product. It has a scalar value of px. So now I'll get px. So that is the projection of position vector p along x-axis. Similarly, if I take dot product jy and p, so I'll get py. What this has now projected this vector p along y-axis. Similarly, pz. Okay, so all the three can be obtained like this. What was IV, JV, IU? So what was IU, JV and KW? So these were unit vectors along UVW axis in the object frame. Okay, so these were unit vectors. Okay, so now let us write this in compact notation like this. So if I can write this in vector form, so you see this is PU, PU, PU. So all PU will come here. Okay. So this was here, this is here, and then PV, PV, and PW, PW. Okay. So IXIU, IXIU into PU, IXJV is here, IXKW is here, and that is how I rearrange that in the matrix form. What effectively this is saying, so this is your initial point, which was initially PU was equivalent to PV was equivalent to P1, PW was equivalent to PZ. Now that it has rotated, so what are my new coordinates along X, Y and Z axis? So this is the required transformation matrix which is able to do that. So what I am getting is projection of position vector P which was initially there along X, Y and Z axis. So this effectively is your new point. So what is it? This is PXYZ. Initially it was PUVW, that was the initial point. So after rotation the new projections are this. So these are the new coordinates. So this is the new position vector also. Let's say. Okay. So this is what is your rotation matrix 3 cross 3. Okay. So that is what was required. So now let us say, can I derive pure rotation about x-axis? So in order to do that, let us start with what we have obtained in this one here, and then can I substitute now? So IU is not changing. IU is aligned with IX, whereas JV has changed. JV has come to a new location. Similarly, KW has changed and it has come to a new location. Okay, and AX, AZ are wherever it was. So it is in the same location. Now, substituting IX and IU here, angle between them is 0 degree. It hasn't changed. So IX dot IU is equal to IX IU cosine of angle between them, correct? So as because angle is 0 degree, so it is 1, and these were already unit vectors. Effectively this is giving you 1, so that came here. Now let us see what is happening to the other parts of the matrix. So this is Ix into JV, Ix into JV. Okay, both are always orthogonal to each other. So if they are orthogonal, angle between them is 90 degrees. So the dot product becomes 0 degrees. Same with this, same with this, same with this. So all these elements will be 0 degrees. Now let us see what are the other parts. Okay. So now what is the angle between JY and JV? JY. Okay. So this was JY and JV. So angle between them is this. Okay. So what happens? And it is rotated like this. So that is as per right hand thumb rule. It is in positive direction only. So it will be cos phi. Okay. So jy, jv both were unit vectors that turned out to be 1 and cosine of angle between them. So that came here. Similarly, when you work out for other parts of this matrix, you will see it is like this. So this is rotation matrix for the rotation about x-axis by an angle. This is it. So it gives you. So there is a very good note over here. Just if I can tell you, this represents x, this represents y, this represents z. So in order to rotate about x-axis, you have to make this 1 and corresponding row and column as 0. And this is the element which will have some changes that is to be taken care of. Otherwise, it looks like this. In general, this is so easy recalling your rotation matrices. Okay, so this is rotation about x-axis by an angle psi. This is it. Similarly, if I can obtain rotation matrix about for the rotation about y-axis by an angle phi, that can be derived using the same startup point, that is this one. If you start with, you will obtain this, and rotation about z-axis may be derived as this. So this is rotation about z-axis, as I told you. So this was equivalent to, this is equivalent to 1. This should change. Corresponding row and column will go to 0. So this is what. So it is cos minus sine and cos theta. Okay. Similarly, in case of y, it is cos sine minus sine cos. Only this has changed its sign. Otherwise, it is same. Okay, similar. So this is what is your rotation matrix. If I write down in 4 cross 4 homogeneous transformation matrix form, it will look like this. So this is your rotation matrix subparts. So this is for this only, but it is in 4 cross 4. This is pure rotation matrix, whereas this is a homogeneous transformation matrix with a rotation matrix submatrix inside it. It says there is no displacement. So there is no translation which is happening. This was 0 only. This was 1 as it is. So this will represent pure rotation matrix in 4 cross 4 homogeneous transformation matrix. Okay, so let us move ahead. So how does it actually look like? So this P has now come to P dash. Projections has changed. Okay, if it is represented in its own frame, the coordinates will remain as it is. So PU, PV and PW will remain as it is. Whereas the projection of U, V and W along x-axis will change. So new projections are Px, Py and similarly Pz. So that is what we did actually. We found out. So P dash is the new point that is obtained by revolving by an angle theta about z-axis. This is your z-axis. The positive direction of rotation is done and you got a new point, that is this. So let us do that. So this is your initial point Px, Py, Pz1. Okay, point in standard frame, the way we will be representing from now on. This is your 4 cross 4 rotation matrix, exactly this one. So if you apply this transformation to this point, you reach to a new location. Okay, so this is the new coordinate of your point. So that is P dash, coordinates of P dash. You can quickly derive using geometrical technique also. You will arrive at this rotated point. So this is how you have to do rotation. Now let us look at composite rotation. Okay, so how to go for it? Let us say you have a point P which is to be applied with rotation about x-axis by an angle alpha, z-axis by an angle theta and y-axis by an angle phi. So how will you go for it? So here goes your point. So this is your initial point given as Px, Py, Pz1. So on this point you have applied first transformation, that is rotation about x-axis by an angle alpha. Okay, you have done rotation about x-axis by an angle alpha. Okay, so this is your required rotation matrix. When applied to this point, you will reach to a new point. Okay, you will reach to a new point. Then you apply the resultant of this. Resultant of this will give you a new point. Now you apply a second transformation. The second transformation which is there, that says rotation about z-axis by an angle theta. Rotation about z-axis by an angle theta. So this point now, P dash is now at, so this was initially P, sorry, this was in, as you use same color, so this is initially P, then you came to P dash. Now P dash is acted upon by this rotation matrix, so you will reach to a new point, that is P double dash, that is your new point after applying this matrix. Okay, and now finally the third transformation which is there, that is rotation about y-axis by an angle phi. Okay, so about y-axis by an angle phi. Okay, you have applied that rotation matrix to the resultant point P double dash, so you reach to a new point, that is P triple dash, that is your new location. So this is how you have to apply. And then in a composite way, if you can multiply all these together, you reach to a new matrix which is known as a composite matrix, that can, in a single operation, this has a capacity to rotate about x-axis by an angle alpha, z-axis by an angle theta, and y-axis by an angle phi. So all the three rotations are now in a 4 cross 4 matrix form. So this is a 4 cross 4 matrix, and it can directly be applied on the point, and you get to P triple dash straight away. Okay. So yes, this is very important to remember, that rotation matrices are not commutative. That means the sequence is very important. Not just rotation matrix. Mathematically, matrix multiplication is not commutative in nature. A into B is not equal to B into A. Got it? So same applies here also. Even for rotation matrix, results are different. So that will take you to a different final composite transformation matrix if you change the order. So if you can try changing the order, you can see where do you reach. Okay, you will see this matrix itself is different, and so is your product of this matrix to your initial point, and finally you will reach to a new point. Okay, you can try doing that using various tools that I have listed here. This can be done using any symbolic computation tool to perform the above task. You can use MuPad in MATLAB if your university has it, or Mathematica if it is there. That is free with Raspberry Pi. Initially it used to come even on Androids. WX Maxima is freeware which is there. It can run even on Ubuntu. It can run on Windows. It can run on Mac also. So this is free. So you can use any of these tools to do symbolic computation. You don't need to have an angle for it. You can directly use alpha, theta, psi, whatever symbols that you want to go at. Let us just see by an example, as we have seen just now. So R, Y, X are in different order as compared to this. Both are not equivalent. Let us see by demonstration. Initially, let us say you were here. Now you have rotated about x-axis by an angle 90 degree, and you came here. Now you have rotated about y-axis by an angle 90 degree. You finally reached here. So first rotation was about x-axis, then was about y-axis. Okay. Now see the change in order. Now I want to rotate first about this part of it. So first about y-axis by 90 degree, and then I have rotated about x-axis by 90 degree. About x-axis by 90 degree, I reached here. So you see the orientation of both the objects are different. The object which was rotated x and y, then later y and x in a different sequence, it reached to a different place. So you see, this is by example, you can just see. Okay. Okay. So now let us see some properties of rotation matrix, and they are very important while we deal with rotation matrix in order to simplify our expressions quite a lot of time. So yes, this was the initial thing that we saw earlier. So PUVW acted upon by a rotation matrix which looked like this, that gave you a rotated point in the frame O, X, Y, Z. Okay, if I want to do opposite, what should be done? So I can write simply like this. So PUVW equal to rotation matrix inverse, if I can take inverse of this, and P X Y Z. So this should be the case, right? Let us say we represent this using a new matrix called Q. Okay, so Q applied to P X Y Z should give me PUVW. Okay, now let us derive this from the first principle. Now what I actually want to do, initially the vector was Px Ix, then Py Iy, then Pz K. So initially the vector was Px Ix, Py Jy, Pz Kz. Okay, so this was your initial vector. Now I have to take projection of this on UVW plane. So I have to take dot product with IU, JV and KW. So three dot products will give me projection of this vector along UVW. So rearranging that this time will take you to this, and this is what you see. This is your new rotation matrix to transform PXYZ in UVW plane. Okay, express Px, Py, Pz in UVW. Okay, so we can simply, we have just taken projections of that. So yes, rearranging that, because dot product is commutative, Ix into Iu is Iu into In. Both are same, so I have just flipped them. Okay, and what do I get? As dot product is commutative, so it is exactly like this. Okay, and what do you see? This column is now appearing here as a R transpose. It is R transpose. So what you find here, something that can do inverse transformation, R inverse is equal to R transpose. So what does it say? Q now is equal to R inverse. It is also equal to R transpose. Okay. So what it is? Basically now QR is equal to R transpose R is equal to R inverse R is equal to identity matrix. So what is it? This is basically an orthogonal matrix. So rotation matrices are orthogonal. Okay, they are orthogonal. Okay, and you will observe also rotation matrices, each of them, as because they are projection of unit vector along x, along y, along z. Each one of them are unit vectors. So this is projection of u along x, u v along y. This is k along z. Okay. So this is what. Okay. So these are three vectors. And overall, again, whole of this is a, if you take determinant of this rotation matrix, it will give you 1. Okay. So you can try doing that. But yes, let us move ahead and just see few notes which are very, very important. If the rotation coordinate system OUVW rotates about one of the principal axis OXYZ, then you saw you were doing a pre-multiplication of previous resultant rotation matrix with the appropriate basic rotation matrix. So what do I mean? So first, let us start with the point you applied a rotation matrix, you reach to a new point. Now for the second transformation, you have to apply P dash with next transformation. Okay, not just rotation, can be any transformation. Okay, so you did this. This is equivalent to R1 into P, and you have second transformation, that is R2. So R1, R2, P. Okay, so because P dash is R1P, I have just substituted it here. You see, you just did what? Pre-multiplied that. So this is what. So you both were in projected on VW. Okay, so this is what is the meaning of this. Next, this time if the rotating coordinate system rotates about its own principal axis, that means once you have reached there, object rotates in a new coordinate system where it has reached. Okay, if this object has come to a new place, let me show you by this. So this is your space. Okay, so initially it rotated about its x-axis, about its y-axis. That is fine. It can do this, it can do this. And let us say if it has rotated here, your x-axis is now along this, y-axis is also inclined. So in this case, what has happened? You see. So this time, if I want to rotate about object's x-axis, it should rotate about the axis which is like this. Okay, so this time it will rotate like this. If it has to rotate with original x-axis, this will go something like this. Got it? So that means object's own axis, if it rotates, you have to post multiply the rotation transformation matrix. Now what do I mean? In this case, instead of having R1, R2 over here, if second transformation is about object's coordinate system only, that means in the new location, once it has reached, object has again rotated, but not with respect to the principal axis, but with respect to its own axis. This time, right? R1 and then you have to do R2. So that the transformation matrices will go in this order. Okay, this is what. Okay. Even in case of homogeneous transformation matrix, you have to do same thing, not just for rotation matrix, even for homogeneous transformation matrix. So you have to go in similar these two order for respective jobs. Okay. So inverse of a rotation matrix is equal to transpose that you saw. It is a orthogonal matrix. So this is true anyway. Okay. Now let us do rotation about an arbitrary axis. Why? So far you know you are ready to rotate about x-axis, you can rotate about y-axis, you can rotate about z-axis. You always have in hand what is known as a principal transformation matrices for rotation. Okay. So now can I rotate about an arbitrary axis? That is very much required. Let us say a robot has reached to a place. Now it doesn't want to rotate about global frame. Rather it want to rotate about its own frame where it is. Okay, so can we do that? So in order to do that, it is a standard transformation technique, not just specific to robotics, I tell you. So it is there in computer graphics also, it is there in animation software, anything. Okay, so same thing we'll be doing here. We'll try to align, let us say this is your object. Let me start with explaining this. So this is your initial vector. Okay, I want to do a finite rotation about this axis, about an axis which is lying in space. It is not aligned with x, not aligned with y, not aligned with z. Can I do that rotation? Rotation by an angle, let's say theta, about a vector which is r. R is a unit vector. And projection of r along x is rx, projection of r along y, ry, along z it is rz. So this you can create a geometrical cube like this of dimension rx, ry and rz for the three orthogonal directions. Okay. So now I'll start aligning this. Now I'll start aligning this to one of the axes. Let us say I have chosen to align this r about z axis. But how will I go for it? First rotation will be, let us say, rotation about x axis by an angle alpha. So what I have done, this is your x axis. You have rotated it by an angle alpha. And what happens, this position vector, this r vector now comes down like this and you come to this location. Okay, and this is your r, the distance that position vector length is not going to change, so it has come to a new location, that is r. Okay, so this is it. So this was initial vector, so this was ry, so that remains as it is. So now this is it. So this is your first transformation, rotation about x-axis by an angle alpha you reached here. Now the second one. This time, and you see you have to follow right-handed coordinate system in order to measure any angle. So it was positive in the earlier case. It was positive alpha. Okay, alpha was positive. Okay, this time I have to do rotation about y-axis by an angle minus beta. Why minus beta? This is your positive direction. But you have to, sorry, this is your positive direction. But I want to rotate this vector now in order to align with z-axis. This r should now be rotated like this so as to come here. So this distance remains r from here to here. Okay, it has come, and thus the rotation is beta angle by negative value. So you have to rotate by minus beta angle. So that is rotation about y-axis by an angle minus beta. So this is your y-axis. So you have to go like this. Okay. So now you are ready to do rotation. Okay. Because now you are ready, you already have a rotation matrix for rotation about z-axis. Okay. That is what you wanted to do. Okay. So this is your second transformation. So the third transformation will be the actual one that I wanted to do. So what I wanted is rotation about r by an angle phi. So this is now rotation about z-axis. So it is this, and it is in clockwise direction. That is counterclockwise. It is in counterclockwise direction, and it is positive. So it is rz phi. So now that I have already rotated this object, okay, this object is already rotated. Now I have to bring back everything to its own place. Okay, so I'll do inverse of this. So this will go here, this will come here now. Okay, you have to come back now. Now that you have already rotated the thing, has to come back like this. This is here, and it also has to come back like this. Again, it comes back to its original location. By, you see, first is alpha, next is minus alpha. This comes here. Beta, minus beta, and beta. It is here. This is your actual rotation that you wanted to do. That is rotation about r by an angle phi. Okay, this is what we wanted to do, and that was done here. So what you effectively did is, instead of, because you didn't had a rotation matrix to rotate about arbitrary axis, you have taken this arbitrary axis to one of the standard axis, rotated it there, and brought it back to the original location. Okay, so this is your steps to do this transformation. Now let us just write all of them. Find out the angles first, because you know each one of them will constitute the elements will be constituted of elements cos alpha, sin alpha, cos beta, sin beta, cos phi, sin phi. So can we calculate all those angles using this? So that can be easily found out. So wherever you see it is just Rx, that means you have in denominator, that is Rx square plus Ry square plus Rz square, because R was initially a unit vector. So this actually is a unit vector, that is 1. So that is why you see only Rx. So let us just find out what is sine beta to say. So this is beta. So sine beta will be simply this distance or this distance. What is sine beta? Okay. So it is, this was initially r. So this is r. Okay. The magnitude of this is r. Okay. And this is your sine beta. Both are same. So r sine beta is this distance, and how much is this? This is rx. Okay, rx by r, rx by r. So this is your sine beta. Now similar one, you can pick up any one of these. So in order to do cosine beta, you have to take this distance actually. This distance actually. What it is? It is ry square and rz square. Cos, when you do cos beta, you are left with ry and rz. Okay. So because ry is now aligned, to this. So this is exactly ry and rz. Got it? So now similarly you can find out other angles too and substitute them when you do actual rotation in your rotation matrices. So this is your order. First you did rotation about x-axis by an angle alpha, y-axis about minus beta. This is your actual rotation. Then you brought it back here. This was brought back here. Okay. So you have to do the reverse transformation. So this is here. So if you substitute all the rotation matrix, it is something like this. Rotation about x-axis by an angle alpha, y-axis by minus beta, you see, and z-axis by 5, again y-axis beta, x-axis minus alpha. So all the matrices are here. Multiplying them together will give you something like this, where V phi is equal to 1 minus cos phi. It is known as versine phi. Okay. So this is a composite rotation matrix. Okay. In order to do in the shortest possible time, maybe this is one of the very good one which is normally used. Okay, in computer graphics, in order to do animation, graphics and all, object transformations are done. That uses this. This is also used in robotics. There is now need to represent orientation in a way, because orientation can be achieved using multiple ways. There are 3 rotations which can be done along principal axis. So now object can rotate about its own axis as well. Okay, so you are now having another 3 axis which is in object plane. So there can be multiple combinations to do rotation in 3-dimensional space. So object may be rotated about principal axis, then rotated about its own axis, then principal axis. You can have multiple combination of those. Total 24 combinations are possible that way. So that is how you can orient any way you want in 3-dimensional space by defining these 3 rotations. Okay, so it reduces the requirement of basically what you saw is the rotation matrix now has 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Okay, 9 elements. Okay, you have to know all of them in order to find out this. Okay, but if you can find out all these elements are not linearly independent, because each one of them are unit vectors. If this changes, these two will also change. Any of these will change, you will see a change in this. So total 3 things can change, not more than that, because there are 3 orthogonal vectors. So that is the reason behind it. So by specifying in Euler angle, there are 3 rotations which are required. That is 3 degree of freedom system. Any object, if it is only rotation which is to be done, it has 3 degrees of freedom. You know that. So yes, there are 3 rotations which are represented as phi, theta, psi. Okay, that can be done in global coordinate system or in the object coordinate system. Okay, so that is what. So there are few important ones which are there. One of them is a gyroscopic one. A gyroscopic one that says rotation about phi by z. This is rotation about universal frame, that is the global frame, that is the principal axis, and then you do rotation in the object frame u direction by an angle theta. Then you do object frame again by an angle phi. Okay, so 3 rotations are like psi, theta, phi. Okay, so first was in principal axis, remaining 2 were in object frame. Okay, now similar is system 2. This is also a gyroscopic system, but instead of u, now you see it is v. Rest everything is same. rotation phi of principal axis, then object axis V, object axis W, phi theta psi. Now this is very common one which is easy to understand as well, that is and yaw axis. We'll discuss all of them in very much detail now. Let us start with system 1, how to go for it. So let us say you initially started somewhere over here. Okay, you initially had your vector which was u aligned like this, v aligned like this, and w was aligned here. Okay, so first rotation is, if you talk about system 1, it is rotation about z axis by some angle. Okay, and then rotation about local frame by an angle, then again local frame by an angle. Okay, 3 rotations are there. So see how it is happening. First you have rotated about z axis by this angle. So z axis by this angle. So what has happened? New location of this is, it has come here. Now V has come to V dash. So U came to U dash, V came to V dash. Got it? This is after first rotation like this. This is fine. Okay, this is after first rotation. Now see what happens once you do the second operation. Second operation will do something else. So it has to rotate about U by an angle theta. So let us see where is U. So here is your U. You have to rotate an angle theta. This time V goes to V dash goes to V double dash. W goes to new location, that is W dash. Not it can be written as W double dash also. So yes, these two will change. So you have reached here, you have reached here. That is your new location once you do this. Now the third transformation, third rotation. So that is actually doing this. So it is rotation about W local frame by an angle psi. So W by an angle psi. This will take it to a new location. This is here. Here is your angle which is here. Psi. This is your new location. So this is where it finally reached. Okay. So this is how it is done. So rotation transformation wise, it is first transformation which is here. Because it is local rotations about object frame, it has to be post multiplied. So it comes here. Next one comes here. Your resultant transformation matrix. If you write them all, so this is your first transformation. This is your second one. This is your third one. Post multiply, you just get this. So this is your composite transformation matrix to do such kind of rotation. This is a matrix which can represent 3 rotations, right? This can represent orientation of an object after 3 consecutive rotations in space. Okay, this is equivalent to, if you look otherwise, if you see, if it is rotated about principal axis, what is it? This is rotation about z axis by an angle phi. This is rotation about x axis by an angle theta. This is rotation about again z axis by an angle phi. Got it? So there are 3 rotations. If you look, if it is in universal frame, that is the principal coordinate axis, it can be done like this. So same position, same orientation can be expressed using principal rotations also, principal axis rotations also. If you can do this, this and this, so you arrive at same result. Got it? So that is what. So this is gyroscopic system 1. Similar is your gyroscopic system 2. Again you have 3 consecutive rotations. First is rotation z axis. This time instead of u it is v and w again. And this is your figure. If you write them together, this is your first transformation. Post multiply second one. Post multiply the third one, as because they are about local axis rotations. And again, if you look at principal axis rotation, which can take you to same orientation, it is rotation about z axis by an angle psi. rotation about y-axis by an angle theta. This is rotation about z-axis by angle phi. Okay, so 3 consecutive rotation taken in this order because it is principal axis rotations. So this also takes the object to the same place, or an object in the place can be defined using this kind of Euler angle, and you reach to a place. Okay, so this is equivalent. Both are equivalent. Now let us look at the third, which is the most important one, that is most commonly used for any floating object in space. So any floating based system like an aircraft, orientation can be only be observed clearly if you can see in your reference frame. Where are you sitting? You are sitting in a global frame. So you can see it is rolling. Okay, you can see it is rolling. It can do back and forth movement like pitching. It can do pitch, or it can do yaw like this. Okay, it can do yaw. Same with any ship. It can do roll. That is rolling, roll. Okay, this is how you can do back and forth again, pitching, and you can do yawing. So this also is popular in marine vessels to express the orientation of a vessel. Mobile phones, you already have accelerometer to measure the angle. So about which direction you have to measure about global axis. That is with respect to Earth. That is with respect to the principal axis. Mobile phones, they also give you accelerometers, can give you tilts also. Tilt angle can be calculated based on accelerometer sensors. Okay, so that can give you angular positions based on this RPY, Roll-Pitch-Yaw, head mount device of a virtual reality system that also can tilt the environment which you are seeing. Quadcopters, that is drones like this, Formula One cars, industrial robots. So industrial robots, basically they use this because it is easy to understand and visualize. That is the reason industrial robots, although the frames are relatively placed, it is easier to express them in roll-pitch-yaw system because apprentices who are programming the robot, they can easily visualize how my robot is oriented if I just say this 3 angles. Okay, and that is how it is programmed. Internally, the robot may be converting RPY that a programmer is specifying to maybe UVW or Euler angle system 1 or 2 or 3, whatever. So it internally may use something else, but externally, in order to program, in order to understand, this is the thing which is used. So this has just 3 rotations which are very, very simple. Rotation about x-axis by an angle psi, okay, or y theta about z phi theta psi. 3 rotations are there, which is enough to express this. So rotation about x-axis, this time you will do pre y-axis and z-axis. 3 rotations are there. Okay. So simply this can be expressed like this. This was the first operation, rotation about x, rotation about y, rotation about z. So these 3 rotations, 3 multiplied, and you arrive at this. Now again, can it be inverted back to a relative frame of reference? Yes, it can be. So this is your first rotation. This is rotation about z-axis. Okay, not this one. So this is your first rotation. This is rotation about z-axis. Then you do post multiplication by this. So it can be written as rotation about theta by v about v-axis and rotation about psi about u-axis. Okay. These are the 3. First one is your principal axis. Next 2 are local. So this is how it can also be converted. Got it? This is Euler angle system of rotation that can represent orientation of an object in space. Okay. So yes, that's all for this lecture. So next class we'll be starting with robot kinematics, TH parameters, and we'll start doing forward kinematics. Okay, we'll talk about that in next class. That's all. Thanks a lot.